Welcome, Mahesh. Welcome, everyone, to the next edition of tinyML Builds. Thank you, Mahesh, for taking the time from your day to be with us. I think we'll have a very interesting conversation.
Good morning, Venkat. Yeah, look forward to the conversation.
Okay. And this would not be possible without our strategic partners, AI-safe analog devices, Arduino, ARM, BrainChip, Edge Impulse, Efficient, Greenwaves, Gravity, HiMax, Imagimob, Infineon, Inotera, Microsoft, Nota AI, NXP, Polygon Technology, Kixo, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST, thanks to you, Mahesh, Synaptics, Sentient, and TDK. I would encourage the audience to join this very fast-growing tinyML community. There are meetup events that you're encouraged to join. If you don't have one local, do feel free to start one up. The tinyML Foundation is behind you to really help you to get involved in this technology. Also on LinkedIn, there's quite a large community, a lot of announcements there talking about the various new developments. This talk, as well as a large number of others, are on the tinyML YouTube channel. These are deeply technical and very little fluff or marketing. So I've learned quite a bit by reviewing some of these. I would encourage you to go and take a look at the YouTube channel as well. We had the tinyML EMEA recently. The next one, next in-person event is coming up in Asia, in South Korea, Seoul. Would encourage you to take a look at this, and the deadline for presentations and posters is coming up pretty soon, August 7th. Feel free to use the QR code or the link here to sign up or to take a look at the agenda. This is something that came up recently. I would encourage you to also take a look at the Edge AI Technology Report. This is a free download, and it's a very broad yet detailed look at the tinyML space, covering a very wide spectrum of topics of interest, not only to technology, but on the business side as well. So it's a very interesting report. Feel free to read about me. I like building stuff, and that's why I called it the Build series. So getting to Mahesh, thank you again, Mahesh, for being here today. Mahesh is Fellow and Senior Director of MEMS Software Solutions at STMicro in Santa Clara, and leads the development of solutions and reference designs for mobile phones, consumer electronic devices, and a variety of other applications. His area of expertise includes AI, ML, MEMS, IoT, and others. So, Mahesh has been awarded 34 patents, and he's a PhD as well. So welcome, Mahesh.
Yeah, thank you for this kind words, Venkat.
So let's get started with the topic that we're going to discuss, which is some of the edge, the processing inside a sensor, right? So we normally think of tinyML as processing at the edge. From talking to you earlier, it seems like you've gone one more step and really pushed processing right into the sensor.
Yeah.
So with that topic in mind, could you maybe talk a little bit about your background and about just an introduction to what we're talking about today?
Sure. Yes. So as you mentioned earlier, Venkat, I work for STMicroelectronics. I'm based in Santa Clara. I'm part of MEMS Software Solutions, and so we build reference designs and help integrate our customers to integrate our solutions into their products. The idea that we have here about sensors and computing inside the sensor, so we call it edge of the edge. Essentially, you are able to compute, you are able to run machine learning logic inside the sensors. We have these solutions that have been adopted into all kinds of applications. So the main idea here is if you do not need to send raw sensor data and conserve the communication bandwidth and thereby improve the power efficiency of the system, this is the right way to go. You can run compute logic inside the sensor and thereby, deliver essential information as and when needed, rather than continuously send, raw sensor data across.
So the way I think of an IMU, which is a gyroscope, accelerometer, and maybe a magnetometer, is typically there's an I2C bus. You send it a command and it gives you back some raw data, and then you process it and figure out whether maybe the device is facing up or down or some orientation. How is this different from what you're talking about?
Yes. So the sensors that we work with, they have these serial interfaces, which can be either I2C or SPI, or latest is I3C. So I3C interface, has its own, great deal of advantages, and that's why industry is moving in this direction to adopt this interface. In case of a regular sensor, let's just pick inertial sensor with accelerometer gyroscope combination. You would configure the sensor for a certain sample rate or output data rate. You would configure the sensor for desired level of sensitivity. In case of gyroscope, you could set the sensor to have a dynamic range of, let's say, 2000 plus minus 2000 degrees per second to you can set this to maybe 100 degrees per second if you would want to have an application where your angular rate does not exceed that, right? So you would have all of those settings that are done at the time of configuration of the sensors over the serial interface. Now, in case of these sensors which have a machine learning core inside them, or a finite state machine inside them, or they could be the intelligent sensor processing unit flavor of our sensors, they essentially would have also one extra step, which is where you download the logic that executes in the sensor at the time of initialization. So if you are planning to run a decision tree inside the sensor, the very first step of initialization at the time of configuring the sensor would also be to download the configuration for a decision tree, or a combination of decision trees, or a combination of decision trees plus finite state machines. So this would also be, the configuration would also include aspects such as whether you are using a meta classifier on top of a decision tree to further smooth the output. How would you want to receive your output? Would it be just an interrupt? As you indicated earlier, you can have a decision tree that can be used to detect whether the device is, let's imagine it's a mobile phone. If it is sitting face up or face down, it could be an interrupt that could be generated the moment you see a change. Or you could configure your sensor to have the output available on certain output registers. And you could raise an interrupt where the application processor would, upon receiving this interrupt, go read those registers. So that's what, is now the process for configuring these sensors and, interacting with them.
Okay. So you mentioned a couple of things, which is sending data was normal IMU would just keep getting data from it.
Yeah.
slightly more intelligent IMU would say, hey, you know what, you crossed a threshold of some kind, so that you minimize the amount of data passing. Eventually, that data has to be processed to get information out.
Yes.
And I think what you're saying is put that, rather than waking up a processor that is going to be consuming a lot of power, just doing this simple task, push that into the sensor itself, where it can be highly specialized.
Correct. Yeah. So let me just quickly share a slide and describe this using this slide. Let me just do that really quickly. So what you see here is a block diagram that can be used to explain this whole notion. You are looking at a block diagram of a sensor with machine learning core. So you have access to the sensor data. It could be an accelerometer or gyroscope data. The device could have an ability to bring in external sensor data. So you can bring in a magnetometer data or pressure sensor data, any other data. And this device has two important computational blocks. One is filters. You would want to process the sensor data with the filters that you select. It could be a low pass filter, band pass filter, high pass filter, because the moment you improve your signal content through such filters, the performance of your machine learning logic, such as decision tree, will improve. Now, the computational block here also contains some predefined features. So as you know, any algorithm that you put together which processes the sensor data would contain mean or variance or energy in the band or peak-to-peak values or zero crossing, all those features. So those are built into the sensor now. So the filtered data is now processed through these features that are already computed, and your decision tree logic will essentially traverse through any new sensor data that comes in, processing a window of that sensor data, and thereby it would generate the outcome. It could be classification for human activity recognition, or it could be just something as simple as detecting devices face up or face down. You can also process the output of this decision tree through a meta classifier. And as I mentioned earlier, the results could be made available in a set of registers, or it could be just an interrupt. So that's basically how the whole device is set up. And all of this does not have, as you can imagine here, you don't have a general purpose microcontroller embedded into the sensor. So what is the biggest advantage here? The biggest advantage here is since these features are built into you can imagine gates, the current consumption for this sensor or the computational part is very, very small. So to give you an example, human activity recognition logic, it can be embedded in as a form of a decision tree into the sensor. It'll consume about 7 to 8 microamps of current consumption. So what that means is that for your always-on devices or sensor nodes in case of industrial applications where your battery is rather small, or you would want to have extended performance of the solution, you can actually do that, and all of this logic running inside the sensor.
So that's 6 to 8 microamps at 1.8 volts.
Exactly.
And that includes the sensor itself.
No, this is only the compute part. So the sensor, okay. Let's say you're operating the accelerometer only, in low power mode, then it would be around maybe another 5 to 7 microamps of current consumption.
Okay, so about maybe 15 microamps at 1.8 volts. That's really impressive because everything else stays shut down. The stuff on the right, the main processor, is completely off.
Correct.
Okay, and so this is, I think the reason, tell me if I got this right. The reason you're doing this is because most of the time devices are going to be sitting, not really doing very much. Even your phone, which is with you, might be sitting on a desk, a laptop or package tracking or something. Most of the time, nothing is happening. So why spend power in the main processor?
Yep, that's exactly the point. If you need the microcontroller primarily to configure this sensor, that's where you would need it to be active. The application processor does not need to process the raw sensor data and let the sensor do all of this computation.
Okay. We have an interesting question that just came up and maybe this is a little out of order from what you haven't talked about this yet, which is does the device need a pre-trained model or is there on-device learning?
Yes, okay. So in this case, for this particular sensor, you would essentially download a pre-trained model onto it. We have, another device which let me just bring up that solution here. So we have ISPU, Intelligent Sensor Processing Unit. So this particular device, essentially, you can run your on-device learning logic on this particular sensor. So you have the ability to run a neural network on this thing, or you can run C code on this device. So essentially, what it has is 32 kilobytes of program memory and about 8 kilobytes of data memory or RAM available to you. And you have the ability to bring in, accelerometer, gyroscope, temperature, or any other sensor data that can be, communicated to this device or the I2C interface. And you can run on-device learning on this particular device.
So this, it almost seems like there are two series of devices. One is where you pushed you've really optimized for power and knowing a rather specific use case, which is the first block diagram where instead of the whole dark blue stuff here with ISP core, all that has been pushed into gates. And this one, which is a little bit more general purpose, where you could do on-device learning, which a little bit more flexibility.
Yes, correct, exactly.
Okay. And how do you expose this related to a question that Joshua just asked is, how do you expose all of this to the user?
Okay, so in case of, let me go back to the concept of the decision tree implementation. In this case, as you can imagine, the pipeline here would be that you can collect data, label that data. You can and we have a tool called as Unico. We have a variety of tools that are available from st.com, Algo Builder, Uniclio, all of these tools. So Unico essentially is a tool that would allow you to collect label data. It would allow you for now even generating a decision tree from this sensor data. It would that decision tree can be generated, and it can be stored in a header file, or it can be stored in a address mapping file that can be used to download the decision tree information into the sensor at the time of initialization. So the whole chain is, you essentially start with, of course, data. And this data can be collected using the devices that we have available through HDKs such as sensor tile that we have available, or it could be, if there is any other data set, as long as you can, have your scripts transform that data to be processed and generate a decision tree, this particular sensor can work with it. Okay,
and how does one go about capturing the data itself? This is pretty standard. Is there anything special about the front end?
Yeah, so the capturing of data, let me take the example of human activity recognition. You can, if you want to consider human activity recognition for a device that is on your wrist, you could wear a, HDK that we have, like sensor tile on your wrist, like a smartwatch. And there's a companion Android app which will allow you to, start logging, stop logging, labeling of the data. And it could essentially be done where you can deploy this to a statistically significant number of users for data sets that are, statistically significant. Now, once that has been done, you would want to, pre-process this data to make sure that you essentially can remove the segments of data that don't match with the labels. All of that can be done. And then, it can be processed through any of the tools that are available. For example, you can use tools such as Weka, or you can use Unico. Unico has the ability to ingest this data and generate a decision tree. And this particular decision tree, now Unico would also convert this into a UCF file, which is a file that is essentially downloaded into the sensor at the time of initialization, which will contain all the configuration information. What is the sample rate? What is the window size? What kind of meta classifier you are using? How you should get your output, whether it is on interrupts or which output registers you would want to read this on. So all of that is done in this manner.
Okay. I guess related to that question again is that format documented somewhere, or is that open, or is it closed?
Yeah. So a lot of this information is published on GitHub. So in fact, we have quite a few application examples on GitHub as well. So I'm sharing my screen here for this. So you can see a bunch of application examples on. So if you and these things are available, I can also put this information in the forum such that it's available to you at a later time. So there are a very wide variety of examples that we have put here, along with an example data set. So let's say you want to look at activity recognition for a mobile phone, or for a wrist-worn device, or you're looking at an example of like asset tracking. There are examples like determining head gestures if you have an AR device, or for an automotive example, like determining whether the vehicle is stationary or moving. So we have a variety of examples here that you can play with and get familiar with this. So they contain one sample log file, and documentation is available as well. There is a wide variety of documentation that's available here. So I'll share this link, and it's very easy to try these out using an HDK like SensorDive.
That's wonderful. So it's nice to always see stuff on GitHub where all the details are exposed.
Yes.
So getting back to your block diagram, I have a question about that, which is you talk about decision trees.
Yes.
Right? There's a lot of noise about neural networks. What was the reason that you picked a decision tree versus a neural network?
Okay, so you can. Oh, I'm sorry, I interrupted you.
Oh, no problem. And what are the trade-offs involved, and why did you do a decision tree?
Yes. So yeah, in case of decision tree, there are certain class of problems where a decision tree is just fine. A decision tree is a lot more intuitive when it comes to the solution that has been generated using the labeled data that you have. There are a bunch of papers that have been published which compare the performance of a decision tree versus a neural network for a class of problems. And there are some problems that you do not need to go the route of neural networks. You can get perfectly fine performance using a decision tree. But then there are other examples. There are other applications where a decision tree would not get you the desired performance. The other aspect about these sensors with machine learning core is that they allow you to download a decision tree and run the decision tree on the sensor. But you cannot run any general purpose code like C code on it. So for that, we have a different device called as ISPU. So ISPU gives you that flexibility where you can run any algorithm, whether it is a neural network or a chunk of C code, which can do things such as sensor fusion, for example, to combine accelerometer and gyroscope data and determine the orientation of the device. So that can be run inside ISPU. So both of the opportunities are available to you. There is a third flavor, and that third flavor is a finite state machine. So a finite state machine is also available to you in these sensors. So finite state machine, in case of a finite state machine, you can imagine you have these different states that are available to you, which you can write a simple logic, like, if the threshold exceeds above a certain, if the signal exceeds above a certain threshold value, it means it's state 1. And if something else happens after state 1, you can go to state 2 and so on and so forth. So a finite state machine is also available to you with these sensors. And furthermore, if these two are still constraining, then ISPU is available to you.
Okay. I think what you're saying is decision tree is, it maps well to low power sensor processing, because you're not really trying to do image processing type complexity.
Yes.
You've chosen a certain class of problems there where decision trees work well. And then you have the state machines for simple things like, was something picked up? You don't really need even a decision tree there. You just need something saying, did the XYZ acceleration change over a certain amount?
Exactly.
So what kind of problems work well for decision trees? Are there particular applications that don't work well for this particular sensor? So that our audience can say, hey, you know what? I would rather use the ISPU rather than this thing.
Yes.
How to make that decision?
Yeah. So decision tree I was describing here again. Let me put this up again here. So here are some examples. If you want to use a sensor to do human activity recognition, or there can be an asset tracking kind of application where you want to detect whether a box was picked up or a box was dropped, or if it's on a conveyor belt. All of this can be done using a decision tree. Examples like if you have a security application for home, like door opening or door closing or door is still, this can be done using a decision tree. Head gestures, vibration monitoring, applications such as yoga pose determination, which yoga pose are you doing? So these can be done using a decision tree. Now, as you can imagine more complex, applications, you can, imagine anomaly detection kind of applications. Those are more suited where, you would use a neural network, where you would, if you have anything that has a greater degree of complexity that is not being able to be captured using a decision tree, can be tackled using a neural network. So here are some examples that decision tree works just fine for them with wonderful results.
Okay. We have a somewhat related question from an attendee, which is, how can we reduce delay after training the model, then deploying the MCU to ensure that the decisions are prompted timely? I'm not sure what they're asking for here. But I think it's, I would interpret this question as really the entire loop of going through collecting data, training, deploying,
Yes.
going back again.
Yes.
How do you reduce that? Are there any hints to developers for that?
Yeah, so for that, you certainly can rely on on-device learning. And, on-device learning in this case is one such solution that we have made available on ISPU. So ISPU would allow you to run that on-device learning logic inside the, let me scroll to this page here, inside the ISPU. Now, ISPU essentially, again, you have to keep this in mind that you're limited by the compute resources, because if you increase compute resources, your current consumption goes up. Here, again, in case of ISPU, you are still looking at single or double-digit microamps of current consumption when you're running such classification logic on it, or on-device learning logic on it. If you take the example of gestures, you can run a gesture recognition kind of an application on ISPU where you are able to detect any of such gestures, and maybe 6, 8, 10 types of gestures, 15, 20 types of gestures, and run this on ISPU core, and do all of this with a current consumption of maybe around 20 microamps of for compute part. Of course, the sensing part is additional to it, but if you're using an accelerometer, that's again and the low power mode, 5 to 7 microamps of current consumption.
Okay. And the second part of that question was, can you give some hints on how I can run regression analysis for prediction? Is that something that you can
on sensor, it is not possible. Because again, as you can imagine, compute resources are limited on this. So you can have, as you can imagine, most of the applications, whether they use ISPU or a sensor with machine learning core, would have connectivity, first of all, to an application processor or a microcontroller, which has greater amount of compute resources available. And many of these devices are then in turn connected to cloud, which is where you could archive a large amount of either process sensor data, label data, and associated models with it. So this is where either you could run the such regression analysis on your gateway device, which could be let's imagine that it's a mobile phone. You do have a capability to do some of it on the mobile phone, or you could run this in the cloud.
So another way to answer that might be, and please tell me what you think about it, is there's a certain class of problems where this sort of architecture works well for, and anything more than that, there's always the I2C or I3C connection, get off sensor, do your high compute, but very infrequent processing there.
Right, and exactly.
This is more of a trigger really to wake up the big system.
Yes. So, one idea to consider here is you're distributing the computing in three different parts. One of them is on the sensor. The other part of compute is on your application processor or the gateway device. And the third part is in the cloud. So once, the processing that involves, large amount of memory requirement, or, you need to have access to archive data, or where you essentially are running, such complex models. So you would want to run that in the cloud. There is a certain other block of processing that can be done on the gateway devices, where you could say, okay, I need to determine, whether the data that I have acquired is new data or is it relevant data. Like, there's no point in constantly sending to the cloud data for the device when the device is stationary, because it would not have any new content in it. So such logic can run on the gateway devices. Logic that determines, if there is a newer version of a decision tree or the model to be downloaded into the sensor, that kind of logic can run on the gateway device. And you could, of course, run a combination of decision trees, finite state machines in sensors that are capable for those, or same thing for ISPU. Here you can run up to 30 algorithms at the same time, as long as they can fit within these compute memory resources.
Okay, I think that's a very good system design characteristic in some sense, right? Use local resources as much as possible, but then always have the ability to punt to the next higher compute, higher memory, but higher energy consumption device up the chain.
Yes.
Okay. I'd like to encourage the audience to ask any questions if they have any. So if in some sense, how do you, if you're putting algorithms in the edge or on the sensor, how do you think about future proofing? For example, if there's a new, when things happen in the field, how do you deal with that?
Okay, so two aspects to this. One is, of course, these sensors have the capability where you could, let's say you're using the sensors with have built-in decision tree kind of a logic. And you're running a combination of decision trees on the sensor, or whether it is, if I take the example of a smartwatch, you could be running logic for fall detection, human activity recognition, gesture recognition, all of those things, in the sensor. Now, and let's imagine that you have an updated model for, human fall detection. So that specific aspect of the decision tree can be updated, and rest of the logic, let's say for human activity recognition, would continue to essentially work as it is. So you have the capability to send this new decision tree to the sensor over I2C, I3C, or SPI interface from the microcontroller or the application processor, and reinitialize the sensor, and thereby, now you have an updated sensor. So this is where the logic running on the gateway or the cloud part comes in. So imagine the scenario where you ship a smartwatch, which has been shipped with factory default settings for your human activity recognition. Now, this particular smartwatch, with a sensor with machine learning core, finite state machine inside it, it can continue to do human activity recognition and continue, and the logic on the gateway device or the application processor can label the data that, okay, I'm detecting person riding the bike, and this data can be periodically, this label data can periodically be uploaded to the cloud. Which is where personalization can be done, which is where you can design a new decision tree for the person, because now you have that specific person's data, and that new decision tree essentially can be downloaded into the sensor, allowing for the device to react to the way the user has been using it. So that's basically how you can have a greatest version of a decision tree or a finite state machine available to you, or in case of ISPU, the greatest network available to you to be downloaded to the sensor, and the sensor then is up to date.
Okay, and for the decision tree, is it accurate to say that you can update a part of the decision tree, only the part that you think, because it is possible to work backwards? It's much easier to compare to a neural network where you can't really update part of it in some sense. You can say, hey, you know what? I can keep this part of the decision tree. This part is changeable on a per user basis. Does that make sense?
Yes. So yeah, that plus the ability to, let's say you are using multiple decision trees at the same time for a problem. Imagine the scenario where you want to have one decision tree to just do activity detection, whether, the person is walking or not, whether the person is riding a bicycle or not. And you can have another set of decision trees, running at the same time doing other classification. So you can just change one part of it and download the new configuration onto the sensor.
Okay.
So the possibilities are quite a few here when it comes to implementing this. So the distributed computing paradigm that I talked about here, it is something that is now allowing for such possibilities to become real, where you can have logic on the gateway, determining what to download into the sensor. And similarly, there is logic on the cloud, which keeps track of what the sensor has, and keeps track of whether I have, essentially statistically significant amount of new data that allows me to improve the classification logic and then download that into the sensor.
Okay. Related to that, there's a question from Joshua, which is, do they allow export of the raw samples to dedicated chips, which is FPGAs, MPU, and DSPs? I think the question is, of course, this is I'm assuming we can export the raw samples, but I'm not
sure. So sensor data is available to you all the time. So you can essentially, raw sensor data, you can configure the sensor to output that, at any time. You can continue to receive your raw sensor data, and at the same time, you can have your decision tree logic, which is running on the sensor itself. So you can do both.
Okay. And so when the decision tree is running, or when you have your ISPU running, the output of that may not be just a 0 or 1, right?
Exactly. Yes.
And so
you can have raw data as well.
So that data is available. So I'm assuming that's what you meant by raw samples.
Yes. So also please consider this, that these sensors also have a sensor hub capability, which means if you have connected a magnetometer, to this sensor, you would also have magnetometer raw data available to you. You can imagine the configuration possibility is there for everything.
Okay. So it's possible to have this almost like your, and not your main processor, but this really sucks all of that logic out of managing a variety of sensors into one place where you can also do the processing on there.
Yes.
Okay. Let's talk about applications a little bit. What do you think are some good applications where you've actually been able to show significant gains over a more conventional um, architecture where there's a sensor and then there's a processor, just data just streams through?
Yeah. So, let me just pick one example for computing devices. So laptops. You can run the logic for determining whether the laptop is on the desk or on the lap using a decision tree type logic, which runs inside the sensor. So you do not need to wake up the main processor for the laptop by constantly feeding it the raw sensor data. We also have the capability to determine whether the laptop is inside the bag or not inside the bag. So as you can, probably we have all experienced this. You close the lid of your laptop and put it in your backpack, and you start to walk away from it, and the laptop does not go into hibernate mode, and it continues to generate heat. So this can all be detected by the logic running inside the sensor. So now, if you want to determine, if you want to essentially improve the user experience, where you are able to detect that, okay, now the person has taken the laptop out of their bag, then you can prepare the processor to be ready, where the user can essentially immediately access the laptop as soon as they open the lid. So such applications are now possible, where you're running the logic inside the sensor, and thereby the battery for the laptop is not being drained by constantly running the main processor. So that's one example where you can immediately see the benefit of this.
Okay, so in that particular case, just a simple threshold is not sufficient, because it's it's much more complicated than just saying, hey, orientation changed, which
exactly
is what sensors were capable of doing.
Yes. So you basically would have, you imagine there's activity recognition logic running, which determines that the person is, walking with their backpack, or the person is on the train with their backpack, or, the person is now climbing stairs to get to their office, whatever the combination may be. So this activity recognition logic runs inside the sensor. The whole concept of determining that, okay, now the orientation of the device indicates that it does not make sense that the laptop could be on a desk in such an orientation. So this could be done using a combination of either a decision tree or a finite state machine logic. But it is not as simple as just thresholding on accelerometer or gyroscope values.
Okay. And I guess one of the more so in a laptop, I don't see it as battery constrained, but there it is the more user inconvenience, right? Where the processor is generating heat, so it just gets hot if it's sitting in a bag, and it's I've had that where it's that the battery just drains and you just pull it out and it's empty. So it's more of inconvenience. However, there are applications where it's absolutely essential to have minimum power, right? Because your entire package is small. Let's say we're trying to do package tracking, for example. It's a very simple use case, but it's complicated from the power point of view.
Exactly. So in case of asset tracking, package tracking, that's where you would want to minimize the current consumption down to bare minimum, and which is what these kind of sensors can allow for.
Okay. There's a question which might be related to how the whole process, which is how do you profile resource utilization like peak RAM usage? I would like to, if you could look at that, but also maybe generalize that a little bit, which is the framework around helping developers figure out whether the really working with the sensor, the tools around it. I think I look at this question as a tool question.
I didn't quite catch the question. Would you kindly repeat the question?
Yes, I think the question was how to profile resource utilization like peak RAM usage. I think it also generalizes further into what does the tool chain look like from a developer's point of view.
Okay, so in case of let's just talk about one for ISPU. So in case of ISPU, you can have your label data available to you. You can use Keras, QKeras, you can use TensorFlow Lite, any of these to generate your neural network. Now that particular network is processed through ST tools, which will allow you to then generate the configuration file for the sensor itself, which can be added to your header file, or it can be a part of your code, which runs on the application processor for initialization, and then that gets downloaded. In case of the tools that are available from ST, it will automatically tell you whether your logic will fit inside the ISPU core or not. Similarly, for decision tree logic, when you use a tool like Unico, it will essentially give you the size of the decision tree. So you can run up to a 512 node decision tree inside the sensor. Larger than that, you cannot fit it inside the sensor. So that is, that's the kind of testing that is done by the tool. To do the profiling, in terms of what would be the compute, ISPU tools, essentially, the tools for ISPU will, give you whether your logic will run inside a certain time window. Because if your logic is, as you can imagine here, you're not running a very complex RTOS on ISPU core. So, you don't have the luxury of what a RTOS will offer to you, but you have to run all of the logic on ISPU within a certain window of time while, you're sampling the sensor data, you're running your processing logic. So all of that is done, all of that is supported by the tool to tell you whether, your compute is taking way too long and that it would cause dropping of samples, because that is not really something that can, give you good performance. So for the logic for decision tree, again, the tools will, allow you to not only look at the expected performance from the data that you have, where you're looking at your training data and your test data. It'll give you all of the accuracy statistics and ability to see whether this will fit inside the sensor or not. So all of that are possible from tools like Unico that we make available for sensors with machine learning core inside them. Okay. You can also play back that sensor data. So you essentially can inject your available data into the sensor and look at the output. So you can essentially really figure out how well is your algorithm working.
So when you say inject data, that is you don't really need to have the sensor in the loop. You have a behavioral model of the sensor where you can inject data and see exactly how much time it will take, what will be the performance. So you don't really need physical hardware. Is my understanding
correct?
That's pretty powerful. So is that an instruction set accurate thing, or?
Yes, the whole idea here is that the sensor data that you have logged, you would essentially be able to see, on each window, what is the classification output. And, the main idea is to be able to catch any of the issues that you probably would have not been able to catch while you were designing your decision tree. So, the ability to play this data back allows you for all of those things.
Okay, wonderful, because then you can take your entire data set and play it back at different models, maybe 10 different models. You have enough compute, you just say which is the best model out there.
Yes.
Okay, that's very useful. A follow-up clarification from William is, is the ISPU able to use other external data sources via the I2C or SPI to drive the decision tree? For example, if the accelerometer detected a human fall and another sensor showed heart rate increase or decrease, would produce different output.
Yeah, so the sensor hub capability allows you to bring in sensor data from other sensors, and the idea here is to be able to run any C logic, if you were to consider that, on ISPU core. So you can do that.
Is there a limitation to the kinds of sensors that can be connected?
Yeah, so certainly the limitation would be number one is they need to support I2C or SPI interface. Number two is the data rates that they are bringing in, because for ISPU core, again, there is compute, but it is a limited amount of compute. You can clock this at either 5 or 10 megahertz. So of course, as you can imagine, this would not allow for using bringing in, like, let's say, an image sensor data.
That makes sense. Yeah, absolutely. Any other thoughts as we start to wrap up?
What I basically want to leave here is the following. You have now a possibility to run these unique algorithms that users can design in sensors themselves. So a sensor now can become, it's not just an accelerometer or a gyroscope. So the sensor can become an activity detector, or a sensor can become a tilt detector, or the sensor can become, a fall detector. So the sensor can be specialized in this manner. And all of this can be achieved at extreme power efficiency, thereby improving the system efficiency. So when the trend is to move in the direction of developing solutions that consume less and less amount of current, for sustainable goals, these sensors are allowing you to move in that direction.
And also, I think to really take it one step further is, I think it allows users to customize what was traditionally called a sensor to do far more without having to depend on a microcontroller and all of the complexity that comes with that, because we've already limited how much compute can be done, right? I mean, there's 5 or 10 megahertz, 32 kilobytes of RAM, 8 kilobytes of data. That forces you to really think very carefully about what you're doing and not just deploy the latest, greatest neural network out there and go crazy with it. There's a large set of problems that need very low power and also customization. And that's something that I think this device allows you to do.
Exactly. You captured it very nicely.
Debbie asks a question, what platform or products do you recommend to help novice developers learn about STMEMS sensors?
Okay, so there are a variety of platforms that are available. Let me see if I can share this here, or I will put this in the forum.
Okay.
We have resources available. We have a whole bunch of tutorials that are available, user manuals and design tips that are available, and there is a community community forum that we have. So you can learn about all of those. In terms of hardware, there are hardware solutions such as a sensor tile that is available. So sensor tile has a variety of these sensors, U5 microcontroller, Bluetooth connectivity, and a small battery in it, which will allow you to configure this device for trying out your algorithms, trying out the solutions that we have published on our GitHub, and there's our Nucleo ecosystem. So there are Nucleo boards that are available where you have a Nucleo board for a specific microcontroller, and you would have a sensor shield that will give you access to a variety of sensors. And we have tools such as Algo Builder, which will allow you to use existing libraries to try them out. So all of this is possible through the available resources which can be accessed through st.com.
Okay, that's great. I've used some of the Nucleo boards and the sensor tile as well. So it's a very useful little platform. Has pretty much everything you need in one little space. Well, I'd like to really thank you, Mahesh, for this very interesting conversation and to really understand how this sort of edge, really pushing the edge right out to the edge, you've been able to accomplish that.
Thank you for the opportunity, and if there are any more questions, we can also use the forum to ask more questions in this regard. We'll try and respond to those questions on the forum.
Thanks to our tinyML strategic partners. This talk would not have been possible without you. Also would like to thank the tinyML organization itself, Olga, and Evgeny, and all the other people who really support us. The executive strategic partners, Qualcomm, AI Research, Sentient, our platinum partners, Atrios, gold strategic partners, Analog Devices, ARM, Edge Impulse, Infineon, Inotera, Microsoft, Renesas, SensiML, STMicro, Synaptics, and we have a host of silver strategic partners. Do get in touch with the tinyML Foundation if you would like to sponsor for the talks and also get involved in the conversation. Thank you so much, and see you soon for the next version.